So let's talk about motion graphs, and let's make that connection again between motion diagrams and motion graphs more explicit. I have an object here that's moving to the right at a constant velocity. We know again that it's a constant velocity because every second shown, it moves 3 units. So it has a velocity of 3 meters per second, and that means that the acceleration must be zero because change in velocity is acceleration, and we have no change in velocity. So going through our the position versus time graph, let's make it green. We know that we're starting, if this is zero, I'm going to put everything on the right as positive and everything on the left as negative. So positive that way, negative that way. And that means that I'm starting at a -9. And then after 1 second, I move forward 3. Then I move forward 3 more, forward 3 more, forward 3 more, forward 3 more. And then at 6 seconds, I'm at positive 1, 2, 3, 4, 5, 6, 7, 8, 9. Cool. Cool. So there's our position versus time graph. We were able to just get it from our motion diagram, or we could have gotten it from being told something like, your object is starting at -9 and moving forward at a speed of 3 meters per second. And then we could have just said, okay, every second it moves 3. So from here, we can use the slope. The slope of this graph represents our change in position. That's how we're changing along this y-axis over our change in time, how we're changing the x-axis, which means it is our velocity vector. And so along this period here, we have a positive velocity of 3. And then the next segment, we again have a positive velocity of 3. And so along each segment that we go, we know that we're always going to have a positive 3 acceleration. I'm sorry, not acceleration, velocity. But we could go back the other direction. If we'd been given the velocity graph first, we can use the velocity graph to figure out position information. So this area here is an area of 3 units. This tells us our displacement, which is the area under the curve. And displacement is our change in x, and we just said it was equal to 3. So if I was told that I started at -9, using this displacement, I know my next one has to be up 3 because I'm changing by 3. And then I change by 3 more, and I change by 3 more, and I change by 3 more. If I really wanted to, I could even extrapolate where I'm at, like way out here, by just saying, okay, it's 3 up and 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 times 3, 27. 9 seconds after here, I should be 27 more positive, which would place me at positive 18. And even though that doesn't show on the graph, that would bear out. So we use the area under the curve on this graph. This is the area under the curve. Is our blah, 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 blah. That is our velocity times time, and that gives us our change in x. Again, it doesn't actually give us our x value, it gives us how much our x changes by. Then moving right along, we have a slope here. Slope. And the slope here is equal to our change in velocity over our change in time. And that would work out to be meters per second over seconds, which is our acceleration vector. So the slope of this graph is going to give us our accelerations. But since I have a slope of 0, this is the world's least interesting graph because it has a constant value of 0. But the same thing that held true with the area under the curve telling us information about the change of that graph is true here. We can once again say that the area under the curve is going to represent the change in our velocity. So that the math works out to be our change in velocity is going to be equal to our area, our acceleration times our time, whether that's a triangle or a rectangle or some combination. Since we have no area here, because 0 times whatever is 0, we're going to have no change on this graph. That means the delta V isn't changing, but the v still stays the same because it had an initial condition of 3 meters per second. That gives us the information that we wanted on this slide. But let's talk a little bit more in some generalities about some of the information you can get from position versus time graphs. So this is another set of graphs. I just cleaned up everything. That's why I had to pause it for just a sec, if you noticed the little skip. But on this graph here, the position versus time, whatever shape that it gives, and I'm just going to give us, I'll actually do a parabola, because I think the parabola tells us some important things and helps us do some important lessons. Actually, I'd like to do that green. Cool. So we have a parabola, and let's say that it has a slope of 0 right at the 3 point time equals 3.5. We'll just save that information for later. The slope of this graph is going to give us the velocity information. But before we even get there, we can, go away. We can use the points along this graph to figure out its positions at time. So all of the points represent a position. I'm sorry, that should actually be backwards. That should be the other way. It says that at a particular moment in time, we have a certain x value. So at 3 seconds, we can look at this and say, oh, I was definitely at around 5 meters. And at 1 second, I was at around 1 meter. And over here at 7-ish seconds, it looks like I was around -9. So that's what the points give us. The slope, once again, gives us the velocity. And then the change in slope actually gives us a little bit more information. If we have something where the slope is going from steep to less steep, or less steep to steeper negative, the way that this is, that would tell us that we have a negative acceleration because we're going from very positive to less positive to now negative and to more negative. Then we could use a changing slope going the other direction to figure out that we had positive acceleration. So the way that the acceleration or the slope changes can give us information about what the acceleration is. It only really gives us the sign, not the exact value, but that can still be very useful. Okay, so our next graph is our velocity versus time graph. And from this graph, even though I'm not going to do exact values, we can see that we initially have a very positive slope. See how it goes up a lot in this area. So I'm just going to put a point here. The exact value doesn't matter, but I'm just saying it's very, very positive there. Then right at 3.5, I have a slope of 0. That means that the object stops moving just briefly right there. So I briefly stop there, and then I start going south again, or down again in the negative direction. So there is the velocity versus time graph that would correspond to that. In this one, our points are going to represent at a particular time what our instantaneous velocity is. If we look at the slope, our slope is going to represent our acceleration. And we can go one step above, something we couldn't do here. We could do the area under the curve. On this one is representing our change in position. Then going over to the acceleration graph, well, this has a total negative, it has a negative slope, but it's always the same slope. That tells us that we have some kind of negative acceleration here. The area on this graph, if I was to do it, you can see that I have a negative area there, and you can see how I have a negative change in velocity. So the area corresponds to our change in velocity. Our points represent at a particular time what our acceleration is. And our slope here isn't going to well, I guess I'll write it in, but our slope represents a physics quantity called a jerk, which is the change in acceleration over a period of time. But jerks actually aren't important in AP Physics, so we don't do jerks in this class. It comes up if you take the AP Physics calculus-based exam, which I should talk to you guys about. The jerk comes up very briefly there, but that's what you need to That's what you need to know for these three graphs. And in particular, I just want to mention one more time this relationship between the parabola and then the linear y equals mx plus b type relationship, and then the negative or positive constant slope. This is a very common like series of graphs. The x can move up and down, or it could flip vertically. If we move it up and down, it has no effect on later graphs. But if we flip it vertically, it's going to flip both of these vertically as well. So that is what we need to know about motion graphs. So thanks for watching.